Basil Hiley was someone that worked with some of us at UCL for over 25 years, I think in some cases maybe 30 years, in terms of Bob Callahan. I had the pleasure of meeting him in 1995 when I did a master's degree at Birkbeck in nuclear and particle physics. And I can never forget the shock of sitting there in the Foundations of Quantum Mechanics lecture and then seeing the polar decomposition of the Schrodinger equation and seeing this term quantum potential dropping out and wondering why in my undergraduate degree at Cambridge I'd never come across it since it was known about since 1952, and it brought an entire ontological interpretation with it. The point of this presentation today is to explore something that came to Basil's attention only a few years ago, which has the irony of being involved in the same 1952 set of papers, physical review, which basically contained the paper by David Bohm and was actually by somebody else, Bryce DeWitt, who was basically starting out on a journey to do quantum gravity. So what I'm basically going to do to go through this is just talk about Bohm's approach. Fortunately, after the excellent presentation yesterday from Chris, I won't need to go into many details. I'm just going to point out a few things that are relevant for doing the comparison and assessing the results of Bohm with the results of DeWitt. I'll talk a bit about how DeWitt arrived at its calculations, but I'm probably not going to dwell on a lot of it because it's a very detailed, very involved set of calculations, and you'll understand why as I turn the next few slides. I'll then give a comparison of what the two quantum potentials that arise are, and then do a bit of a, well, that was then, this is now, what's happened since then. So that's the plan. Wow, right, got it, I think, got it at last. Okay, the paper I'm talking about is Physical Review, 1952. The thing that's interesting is it was in the same volume that David Bohm's original 1952 paper, the two papers, the MD paper on entitled Hidden Variables. Very bad choice of name because that really coloured a lot of the physics community's view of his work, but it's not so much the title that matters in this case, it's the underlying detail. And then it talks a lot here about isomorphisms between groups of point transformations in classical mechanics, translating over to quantum mechanics and actually being a subgroup of the point transformations being basically unitary transformations. And that's a lot of group theory jargon. The bottom line is you're trying to conserve your physics, and point transformations are when you do coordinate transformations in classical mechanics that preserve Hamilton's equations. So effectively your dynamics and your physics is going to stay the same, which is what we would expect. You wouldn't expect your physics to change just because you change your coordinate system, particularly not if it's rectilinear and Euclidean. But obviously in terms of general relativity, things started to become a bit trickier when you talk about the group of general coordinate transformations. And what DeWitt was trying to do was to make those first forages into quantum gravity by saying, this time I'm going to start closer to quantum mechanics, to where the Schrodinger equation is, and try and look very hard at the Schrodinger equation and figure out how I can make it work under curvilinear coordinates. And so that's why some of the mathematics is kind of a bit involved, but hopefully you'll be able to bear with me. That's it, got it. Okay, the basic approach done by Bohm, which was outlined yesterday by Chris, is to start from the Schrodinger equation. And because you're expecting the wave function to be a complex function when it comes out, you would normally on this side be looking at a psi real plus a I psi imaginary, and equating that to a polar decomposition. And as Chris went through it yesterday, you get to the end of this process and you end up with two equations. The top one is a continuity equation by equating the imaginary parts, and you have to go through a lot of things to do with probability flux to get the answer, but essentially that's what it is. It allows you to look at the evolution of your wave function. And then the interesting bit is you get a Hamilton-Jacobi equation when you equate the real parts, and you have this term, which is the quantum potential. And Chris did some amazing things showing when you plot that and the trajectories that come from there. And indeed, one of the other talks did pictures of the quantum potential, and you can see the topography of the quantum potential. You have singularities and all sorts of interesting things in it. But that form is what Basil and Bohm looked at, and Chris and the team, for many years, and demonstrated that it gives the same answers as normal non-relativistic quantum mechanics and the standard interpretation, but trying to understand where it comes from, what it adds to the description of looking at it in this formulation. Things to note, and Chris pointed this out yesterday, those two equations are coupled because the R and the S appear in both equations. So that's not a point transformation. DeWitt basically was trying to look at doing this quantization for gravity, starting from the basics of the Schrödinger equation. And he had these four objectives. Now, I'm not really going to go through the objectives in detail, other than to say, he's in stating the objectives in the paper, he pointed out that he's going to end up effectively with an h-bar squared q term. Now, that q is very similar to the q from the face of it in Bohm's work, but the thing is the h-bar squared has been taken out of the q, so that when you look at that term, if h-bar goes to 0, there shouldn't be any quantum mechanics. Essentially, the task he's doing is trying to move from rectilinear coordinates to curvilinear coordinates and find out what that Schrödinger equation needs to look like to achieve that, and to basically leave the dynamics invariant. We're going to spare you a lot of pain, because I went through quite a lot of pain, but with great help from Bob Callahan, Peter Van Riet, and shoulders to cry on, like Rob Flack's shoulder, when I try to get my head around it. But essentially, what DeWitt does, his starting position is to say, I can write an eigenstate, I can write a state vector as the sum of the eigenstates, and then make it into a wave function by applying the notorious bra, so that you basically use the Dirac notation to call it equivalent to a wave function. And then he basically integrates over the space, and in terms of doing that, he needs to talk about adjacent points, x prime, and he does that using a normalization condition, and that normalization condition starts with a normal Dirac delta function. Not going into the details of it, but he then converts it into a generalized delta function, so you can get into more analytical form. And by doing that and integrating over volume elements, when you move from the normal volume element of d omega to a dx, you end up having to put a metric in it. And so that metric creeps in, the Gij, and that's how he starts off on the game of being able to say, as I move from point to point and I'm looking at constructing my wave function, if I make everything behave properly with my generalized Dirac delta function, I have to then learn how to work in the impact of that, the Gij, from point x to x prime. Now, I'm not going to go through the full detail, but the bottom line is when you do it, you end up with the x is straightforward, but what is less so is the momentum, because he has to go through quite a lot of work to establish that it isn't as simple and straightforward as you would naively expect, that the derivative here, the partial derivative, just gets replaced by a covariant derivative. It doesn't, because you get different results as you come in, because with the delta function, the answer's got to be the same coming from the x to the x prime as from the x prime to the x. That ends up bringing in a factor of a half and a contracted Christoffel symbol as opposed to the full Christoffel symbol. And it's then trying to work out how that differs from what you would normally get in general relativity. Once he's got to the position where he's got a momentum, a form that should be able to be translated into the Schrodinger equation, because you're just now saying it's I h bar whatever your function, whatever your momentum is. So I should go back. So it's I h bar times. So you take that h bar out there, and then that thing is what you would normally look at as your del for calculating your momentum. So that allows them to be into position to start talking about dynamics. So he takes the classical Lagrangian normal form, and then looks at how you convert that into Hamiltonian, which is again it's all classical mechanics and straightforward. However, when you start making your transition to quantum mechanics, there's a bit of nervousness about what's going to go on with the derivatives here. And also, one of the problems is with the order of a function that depends on x's, which is your metric, and this derivative of a function which depends on your metric, which is a function of x's, and then you're going to be doing derivatives over that. You're kind of nervous about having some caution with doing it. But what he does do in the end is he works out that because of the nature of the metric and the fact that that will vanish in certain instances, and also that when the indices are upstairs is the inverse of when the indices are downstairs. He basically has an argument for why you can symmetrize it. And once you symmetrized it into that, by swapping the order of the Gij and the Pi, it then becomes more straightforward. Now, apologies for this, because this seems to now, I've got a, yeah, that's correct, yeah. So you then get, when you're looking at, you're trying to effectively replicate the kinetic energy. So the Pi, the double Pi psi is equivalent to what you get when you do the IH bar grad twice in the Schrodinger equation. And what he's trying to do here is he's saying that if you go straight over to that, or if you go straight over to that for just the II, it would be a partial derivative with the old school notation where dots mean a covariant derivative, commas mean the partial derivative. And then if you're doing the curvilinear, you've got to do all of the components in the metric. Really, what you're talking about is a Pi, Pj of psi is going to have the covariant derivative. And that should handle the curvilinear, the transition to curvilinear. Now, given that is defined as momentum vector, momentum differential differently, what he does is he looks at it, and I apologize for bad notation there, it's slipped up. That should actually be a dot. That's a more modern way of saying a covariant derivative. So he's looking at the difference between his symmetrized kinetic energy term, if you like, and the new momentum operators, and what would have been there if it was the covariant derivative that was going to be your answer. And when he works through it, he ends up finding out that he's got something with 2 mu, which becomes mass, but basically h bar squared times a q of the wave function. And obviously it's a lot of accounting to work through the Christoffel symbols and the contracted Christoffel symbols, but essentially that q, the form of that, and this has been checked and worked through by Bob and Peter to great detail, and I just about managed to hang to the coattails to follow it. But basically, that form doesn't look very geometrical at first, but because of the nature of what the Christoffel symbols are, it is a geometrical object, and that is, when you multiply by h bar squared, a quantum mechanical potential that when you put it back in and do your t minus when you move from your Lagrangian to your Hamiltonian, this is the form that you end up with, which looks very similar to what you would expect classically, plus the classical potential, but then the extra term, h bar squared q, looks suspiciously like Bohm's term.
The question here.
Yeah, go for it.
So he brought it in bit without thinking of polar decomposition.
Yeah, no, oh, that's the whole point. There's no polar decomposition. That's the key point. Thank you, Sylvester. Yeah. Well, that's the question. Is it the same thing? And obviously, when Q goes to 0, the Hamiltonian's classical. So it feels like it ought to be a term that is linked to something quantum. However, so it's not very transparent when you look at that, and evaluating the Q's with the Christoffel symbols is pretty painful.
Yeah, sorry. Just to make a note also, this is the quantum potential that appears in the Hamiltonian.
Yeah,
The
not
Bohm
the
picture, that's a Hamiltonian, the classical Hamiltonian Jacobi. So this one is really the difference. There's an ambiguity in the paper itself. The PIs and the PJs are not in curved space there.
Right.
Yeah.
It's the notation in the paper was a bit ambiguous.
Yeah, it requires careful tracking through to do it. It's tricky, but as I say, we kind of worked. 3 of us have worked through it effectively. I can't claim completely independently because I did get some pointers, but there's some identities you have to derive that are really not straightforward.
But you don't use it twice, right? So once you have it from here,
yes,
now use it, you won't use it again.
Yes, exactly. And then it's evaluating it, but it's also notorious to figure out situations where you'd want to attempt to evaluate that as a quantum potential to calculate it, because obviously with Christoffel symbols it's painful.
Is 13 the Schrödinger equation?
No, it's just saying the difference between, if you look at the del squared part of the Schrödinger equation, it's saying what the difference is between a del squared, that would be my normal rectilinear del squared. Well, it's not.
It's the curved.
Yes, it's a curve.
Curved
Yeah.
del squared.
Yeah.
Right.
That's the curve del squared.
And the curved del squared quantum form.
Yeah.
And that is taking the difference between those two.
And then saying that the difference is this quantum potential.
I was wondering, the other day we were talking to Peter that how the quantum potential arises naturally in the polar coordinates, but not so naturally in other cases. So is this sort of having
No,
No, what you can see is that effectively it is a different quantum potential. It's not the same as Bohm's quantum potential. However, if you work through it during this derivation, the precise form of psi, which is deemed to be a scalar, does not affect DeWitt's analysis. So it doesn't change if you then do a polar decomposition after that. You're just going to basically say in the curvilinear coordinates, you've got an extra potential, which is this h bar squared is q as opposed to Bohm's q. Now, that has some interesting consequences, which I'm going to talk to Yvette about later, as to we are a hell of a lot further on in terms of sensitivity of measurements than we were in 1952. So it would have been inconceivable to see if you could actually measure this and do it. Whereas what jumped out today in your talk was maybe that's a possibility. Now, I'm not an experimental physicist, so I have no clue how you go about designing it, but I recognise the sensitivity of the things you were discussing.
And so on a historical point, then, isn't that why, as I recall conversations with Basil I had about this, isn't that precisely why Wheeler effectively brushed the term under the carpet, because it would be in principle architectable?
I believe so, because I mean, what's going to come out of this in a minute is the relationship between DeWitt and Wheeler.
Yes.
Because I think I've pretty much covered all those points now, except I'll just do the last point. A polar decomposition on a Euclidean manifold results in the bone potential, and it's definitely not a point transformation. So without any doubt, because ending up with two coupled differential equations, through equating real and imaginary parts after applying, differential operators right the way through the original equation, and then tying the parts back together is not there's some symmetry involved in that and some other subtleties that I as yet have not got to the bottom of. It's obviously something that's a group we're going to look at because we want to continue the work that Basil did.
Because on the previous slide,
Yeah.
You say it will go to 0 as h.
Well, anything multiplied by h bar squared, because the form of quantum potential as well that DeWitt uses, it's in terms of dimensionality not the same as Bohm's, because the h bar squared appears within for the Q that Bohm uses. It's just semantics. It's just notation. You just move the h bar squared out, but still the same argument would be if h bar did go to 0. Not that that's necessarily what Basil believed in, because he believed that the world was quantum first and classical second. So it's even if you go to try to argue h bar squared goes down to 0, the quantum world will follow you all the way down.
Right.
So
Just to clarify something. So if you were solving in rectilinear coordinates, this does not appear. Only when you transfer
which is a clue that's a different quantum. Yeah, exactly.
Sorry, in rectilinear coordinates. Oh no, sorry.
Yeah.
No.
Q0, the Q0, or DeWitt's Q0, but the clue is Bohm's isn't because it's in rectilinear coordinates first.
But if you have curved space-time, then you necessarily will come. Because you have to.
Yeah. And if you have a sensitive enough to be able to measure it, you might actually be able to do it. So I think to Mike's point, it could be one of the reasons why DeWitt didn't pursue it, because I'm going to talk about what happened next.
And also I imagine you're also somewhat going to mention the connection with the Coriolis forces, which
I could do, okay, right. If I the way, right, a simple way of trying to hint at that, but I'm not going to address it directly here, is even if you're in Euclidean flat 3 space, if you do your quantum mechanics on a shell in that space, you bring curvature in. So effectively, the things that would be the Coriolis forces that Basil used to refer to are the things that are constraining you to the surface, and then then curvature will pop up.
No.
Yeah.
So just to clarify there, if you start off in rectilinear coordinates, but you transform to some kind of polar coordinates as a point transformation, as a what happens?
Q will be 0. I'll be trying to get the Christoffel symbols to work for it, but I'm pretty sure it'll be 0.
So even if you go to stretch spherical polars in Rn, you still get 0 for your
Yeah. But not if you embed a surface, a low dimensional surface and high dimensional surface, and the constraining of doing that brings in genuine curvature for that dimension.
Could that be why that the effect appears when you switch the polar coordinates in the version, or?
It could well be, but I mean, as I say, we've made. It sounds crazy, but putting the pen to paper meant that we had lots of discussions and sort of, realised some subtleties that we've missed, and that we hadn't got to. Maybe Basil got there, just didn't say to us, but we didn't actually get to discuss that. Okay. Right. What happened next? He didn't do anything with the quantum mechanical potential, DeWitt. He did stand by the analysis that he did, because he repeated it 5 years later in a 57 paper called Dynamical Theory of Curved Spaces. And basically, he set out to do 2 papers to start to do the whole thing again. But in this case, he didn't mention the quantum mechanical potential at all. But literally, it's like almost lifting 3.5, 4 pages of calculation and analysis, changing some things around, I mean, he called some functions R, but by then he realised R is important because the curvature tensor, so changing the symbol to phi and things like that. But essentially, he used it and he furthered it. And to Peter's point, he didn't really dwell on the Hamiltonian in this paper 5 years later. He looked at the action and the Hamilton-Jacobi equation, and that's what he was really focused on in that paper. Okay, and then, but the H bar squared does appear in it because he was being influenced by, I think, Wheeler and Schwinger, and he also looked at Feynman quantization. And when he was trying to apply the same thing to the Feynman quantization, he ended up with a term that was the H bar squared times the scalar curvature, which was one of the things that Basil was looking at for that quantum potential, because it is linked to curvature. And then historically, the 52 paper doesn't get the mentions that 57 does, because the 57 paper was adopted by a community of physicists who started to look at the covariant Schrödinger equation, and that activity goes on to this day. So I can't say any more about where it went to because I don't have time to go through a big literature survey or review of all of it. But there is a kind of cottage industry working on that. What happened 10 years later was the mammoth work that DeWitt did, which was on he did a trilogy of papers called The Quantum Theory of Gravity 1, 2, and 3. This one is the canonical theory, and this will be more known to our community. Not well known to me because I'm not an expert in quantum gravity, but basically in that paper, that's the Wheeler-DeWitt equation, and that didn't really have much practical value at the time, which I'll show you now, because if you look at it, this is from a paper on the archive from Ravelli, where he did a potted history of quantum gravity. And what Wheeler was doing originally was in what Ravelli quaintly refers to as prehistory. And then nothing was done on that till you hit the Wheeler-DeWitt, which is 67. And then nothing is done on that till you get all the way to loop quantum gravity for the Wheeler-DeWitt. A slight that's kind of a detour was mini superspaces, which is what DeWitt did, because he could get an application for that and try to apply it. But the Wheeler-DeWitt equation, that's the Wheeler-DeWitt equation. He refused to call it that. Eventually, in the end, it crumbled, and the community told him that's what we're going to call it. And the DeWitt metric is notorious because what isn't here is there are some constraints you need to apply to it, which are momentum constraints, and they're pretty complicated. So this is just a summary of what we said. Probably won't really go over it because I think I think it's pretty good about the fact that they're not the same quantum potential. But then that does lead to the questions of how, if the two are related, or how are they related, which somehow means if there is a quantum potential that's related to geometry in terms of curvatures envisaged by manipulation of contracted Christoffel symbols, and that's the source of that quantum potential multiplied by h bar squared, where's the geometric origin for the quantum potential on the bone? And that's something that Basil has been searching for a very long time. And I'll even refer to this paper, one of the last ones he's published, which I think you can get on the archive, which he did with Glenn Dennis. De Broglie, general covariance, the geometric background to quantum mechanics. And he looks at sources of curvature, and there's even a source of curvature in Berry's work on optics, which is essentially classical. And I say essentially classical because electromagnetism can be viewed as photons, so can you ever really have a truly classical electromagnetism? I don't know. But essentially, he's explored curvature and things that look like the quantum potential there. This was included in it, but as I say, he didn't make the references there to the fact that the Q for DeWitt will be 0 on a flat space-time. And then measuring it, I think the sensitivity of measuring DeWitt's quantum potential and the arising curvature should be maybe something that can be attempted today and would stop the objection that may have been given by Wheeler. And also there was a case where he evaluated the Q, and it was for a particle moving on flat space and then going over a hemisphere bump, and basically saying it's flat, flat, flat. You get a bit of curvature, evaluating it, and maybe that could be done in the laboratory. I don't know. As I say, I'm not an experimental physicist, so I don't know the scale. And I think I'd like to obviously thank the team at UCL, and last but not least, the benefit of literally hundreds and hundreds of conversations and masses of time spent with Basil Highway.
You show again the quantum, the width wheel there.
Yeah.
There is something, because that's their equation, but they also talk about a quantum potential in their formalism. What? Because that seems to be indeed what's being referred to by a lot of papers.
Oh, right. There are a lot of papers where the cheat is what people have done is they've said, look, if it's a wave function, because they call it wave function, in some cases they call it wave function of the universe, by doing a polar decomposition of that, when they go through that work, it's more Bohm than DeWitt, but it's starting from a different place. And the constraints of the DeWitt metric and the momentum constraints for that, it's going to take a long time to work through the polar decomposition for that. Yeah.
So with the form of the DeWitt potential in terms of the symbols, is that linked to anything? I used to claim that was the Richter scale. So I think, or we have no that would say that was the
It's got to have a geometrical that's what believe it's a geometrical source. We all think it is. We're looking for it. We're trying to get better understanding. But what does curvature look like spread across two variables that are coupled across two different equations? When we figure out the answer, you'll probably be part of that, letting you know. Any
So, is it possible to equate these and find an effective psi for the curvature or coordinate induced? So if you can find an effective wave function, as if the wave function is creating, is it possible to find an?
Well, I believe it would be, but I haven't calculated.
Because that is a very good way to do quantum gravity, right? Because then the curvature is
But I mean,
coming
if
from a
you
psi.
can measure it, is what I'm saying.
Yeah, so, that is also there. But you can just do quantum gravity if a psi can give you that. If you can equate it, I don't know whether you can do
I
it.
think it's amazing. You can have both.
Yeah,
we'll
we
get
can
that.
have both. But what we are regarding usually as a classical background, if you can find a psi for it, then
Yeah.
that is quantum.
Okay, something that would have kind of both quantum potentials the same,
Right,
like
Yeah, two quantum potentials interacting. Yeah.
and they would be the same because they will represent the same
Okay.
They would influence the phase of the wave function, but the issue is whether you can find circumstances where you can suppress one to highlight the other. Because now you know the two, you can start to try and figure out circumstances where one is going to be more prominent than the other.
Okay.
But again, I'm not an experimentalist, so I have to leave it to that's above my pay grade.
Okay.
Any more questions? Any more?
No. That's all. Thank you.
Thank you. Thank you. Thank you.
Thank you.